We took the exam and all that good stuff. So chapter 14 I put up there as a recorded lecture. It's not too long, I don't think. So make sure you do obviously watch it. You're responsible for the information that's in that video. So we're going to pick up here, as I mentioned, with chapter 15, which is solutions. Okay, so let's talk a little bit about aqueous solutions. Aqueous solutions, pretty much most important biologicals and a lot of chemical reactions happen in the aqueous solution. When we talk about solution, it is really the guys that get the aqueous symbol next to it. And that usually means sort of a water environment. And it usually means that basically something was taken and dissolved to make a solution. I think we might have talked about it earlier, but just to remind you that when we talk about sort of a liquid versus sort of something that's aqueous, there is a difference. Although they both are sort of in the liquid state, a pure liquid is just that. So something that has the L is a pure liquid. And that would be, again, something like if you just had water by itself there, would get the liquid symbol. Now, a solution or something that gets the aqueous symbol is really when you take something and you kind of dissolve it into something like water. So if we took the water and we took some sodium chloride, which was solid, and we put them together, the sodium chloride would dissolve in the water, and we would get a sodium chloride solution in this case that would get the aqueous symbol. So again, it can be something with sort of an L next to it. It usually implies that it's just a pure liquid by itself, nothing else sort of mixed in there. But again, you see something with aqueous, I won't say 100% of the time, but most of the time it is sort of like a water sort of environment is the major part of it, but something sort of dissolved in it. A solution actually is a homogeneous mixture, so it does look the same throughout. There's really two parts to a solution. The first part of a solution is what's known as the solute. The solute is the smaller part of the solution. So it's usually the substance that is sort of dissolved. And it's usually that substance that's dissolved in the larger part, which is known as the solvent. So both the solute and the solvent together make up a solution. So you do need, obviously, both of these guys to make up a solution. In my example up here with the sodium chloride solution, the solute would be, and the solvent here, these would be the two. Pick it up. The easy way to sort of know what the solute is in a solution is the name of the solution. So if you have a sodium chloride solution, then it's sodium chloride is your solute. If you have a calcium chloride solution, then calcium chloride would be your solute. So the actual name of the solution, formula that's in front of the aqueous, is always really what the solute is. Again, not 100% of the time, but a lot of times, especially if it's ionic, sort of a compound, it's probably going to be your solvent. So water is definitely a very good solvent, as we'll talk about, for things that are ionic, for things that are polar. So definitely your solvent. And again, whatever the ionic compound would be your solute. Any questions on that there? So as I mentioned, water, again, is not 100% of the time always the solvent that's used, but it is a very, very effective solvent. It's a very effective solvent because really water is polar, as we talked about. So when we think about water, because it is polar, there really is a side to water that is more positive and a side that's more negative. So our kind of hydrogen side of water overall is more positive. The negative side of water is more negative. I'm sorry, the oxygen side of water is more negative there. And that makes it really good for ionic compounds, because ionic compounds are basically ions. And pretty much how all things interact with one another is through what are known as intermolecular forces. So intermolecular forces are basically how all molecules interact with each other, both themselves and how they act with other molecules or those forces. And really all sort of intermolecular forces, which are those forces between molecules, they all really boil down to just a basic connection of like the positive side of one is kind of attracted to the negative side of the other molecule. So when we do something like put sodium chloride into water, what happens is it will break apart into sodium ions and also chloride ions. And what will help it dissolve is the negative side of water would be attracted to the positive ion and basically surround it. It's also how it kind of plucks it out of the solid as it goes and starts surround it. And then the positive side of water would then be attracted, which is the hydrogen side, to the negative ion. And that does two things. That basically allows something like sodium chloride to dissolve. We usually aid this, right? Because we start to stir. We're throwing a bunch of water molecules all over the and allow them to kind of pluck off each of the ions from each other. And we also that allows it to dissolve really easily. This is also why when we talked about way back when, doing something like this is really just a physical change, although we don't see the sodium chloride still there in a solid form. It's basically kind of dissolved into the water matrix. So there's just so many water molecules, we can't visually see it, but there in this sort of sodium chloride form. Again, we knew that we did some experiments early on when we evaporated off the water at the end of the experiment. Water at the end of the experiment that allows the ions to come back. And then we were able to re-achieve our solid that was dissolved in that sort of sodium chloride solution. So water works really well. There's basically an idea in terms of solubility that things that basically have similar intermolecular forces, things that are able to interact with other molecules the same way that they're able to interact with themselves, are very soluble and really will mix really well. When you sort of put together that, really using different types of ways to interact, that's really where you get into trouble and they don't start to mix or be soluble in one another. So this process that I just sort of drew is sometimes referred to as hydration. And again, there's just so many water molecules that surround these ions, it sort of visually disappears from us when we dissolve the solid. And once again, as I mentioned earlier, if we did the process where we evaporated off the water, we would basically evaporate off all these water molecules. That would then leave the ions able to come back together. And again, you would see the solid reform at that particular case. And again, that's why, again, making a solution is really just a physical sort of change, no chemical change occurring here, even though things sort of disappear. Any questions on that there? Here is basically the process at which, we sort of dissolve a solid. This, by the way, is what an ionic solid looks like. It's basically a bunch of stuck together based on opposite charges. And that's a really, really strong attractive force. But again, when you put it into something like water, there's just so many water molecules there that able to really sort of pry off each of these ions here. Here comes some water molecules in to pry it off and surround them as they come off. And like I said, as you sort of mix, you add a little bit more energy. You also throw water all over the solid and allowing it to really start to dissolve really, really well. So on previous chapters, we talked about different compounds and its effectors and solubility. Ionic compounds, again, is usually between a metal and a non-metal. Remember, what is holding that together is the positive negative attraction, which is known as electrostatic attraction. It is a really strong force. That's actually what is sometimes referred to as an intramolecular force, which I believe is in chapter 14, some of that. Intramolecular force is the force within the actual molecule. It is the force that holds one molecule together, not with another molecule, which is actually what holds that sort of individual molecule together. And in ionic compounds, that electrostatic attraction, which is a really strong attraction. As molecular compounds is what we talked about. They're held together by covalent bonding. And that also is an intramolecular force. So that is what holds that together. So both of these are really intramolecular force within the molecule that holds it together. So for example, if we had a water molecule, the bond between the oxygen and hydrogen bond in each of those cases is a intramolecular force. It is basically the sharing of those electrons. When we get a bunch of water molecules together, what happens is the negative side of one is attracted to the positive side of another, and we get some bonding that occurs between that. That is what is known as hydrogen bonding, and that is an intermolecular force. So the bond that holds between this entire water molecule and is an intermolecular force. And in this particular case, this is what is known as hydrogen bonding, which is a relatively strong intermolecular force. As you will hopefully watch 14 there, in terms of intermolecular forces, there's really a few different types. There is hydrogen bonding, which is kind of the strongest. There is dipole-dipole interaction, which is also relatively strong. And then there is dispersion forces. So these are three intermolecular forces, and they each sort of go with different sort of compounds. So let's do this here. So hydrogen bonding is a polar molecule that has the ability to hydrogen bond. And that means that there is a bond between hydrogen and nitrogen, oxygen, or fluorine. So in order for something to have the ability to hydrogen bond, it needs to be a polar molecule that has a hydrogen that's bonded directly to a nitrogen, oxygen, or fluorine, like water. Water, right, has a bond between hydrogen and oxygen. Fluorine are the most electronegative atoms, which makes that OH bond, for example, very polar. It makes a really nice, strong attraction force between them. Dipole-dipole interaction is really where we have polar molecules that cannot hydrogen bond. So this is the main force for polar molecules that really cannot hydrogen bond. And for example, just randomly off the top of my head, we'll draw something like this. So this guy here, which would be a polar molecule, it does not have the ability to hydrogen bond. You may say, well, isn't there a hydrogen here? And there is, but that hydrogen is attached to a carbon, and the carbon hydrogen bond is non-polar, which means that hydrogen is directly bound to the ability to hydrogen bond. So molecules that have hydrogen, but they cannot really do hydrogen bonding. And dipole-dipole is really the main force for polar molecules, as I mentioned, that really cannot hydrogen bond. And it still is a relatively strong sort of force. Then we have dispersion forces, which is really what nonpolar molecules use. So this is really the intermolecular force between different nonpolar molecules. And they are actually really weak ones. They're very, very weak, and they're temporary. So what can happen, for example, is if you have a nonpolar molecule, it has no charge. So just temporarily, for example, the electrons could decide, well, we're just all going to kind of come to this side of the molecule. And what happens when that occurs is temporarily, that guy that normally doesn't have a charge will temporarily gain a positive side and a negative side to the molecule. And if it happens to be next to another nonpolar molecule, it will do kind of the same effect to that nonpolar molecule. Now, these guys that normally would not have a way to interact with each other can temporarily interact with each other because of the shift in the electrons. That's what's referred to as polarizability, the ease at which electrons can kind of move from one side to the other. These are weak because what will happen is those electrons will move back, the charge will kind of go away, and they'll break apart and new ones will form, and then those will kind of go away. So dispersion forces are really, really weak intermolecular forces because they rely upon really temporary changes in the molecules to allow things to interact with each other. And different than any polar molecule, because a polar molecule will always have a separation of charge no matter what the deal is, because it has a dipole moment. You can do whatever you want to it. It will always have the positive side and negative side. It will never go away. And that's why they're much, much stronger. So dispersion forces are the weakest, and hydrogen bonding is the strongest. And this guy is pretty strong too, dipole-dipole interaction. So there's a couple of things that, again, intermolecular forces are important for. One thing is things like boiling points and melting points. So the stronger the intermolecular force, the higher the melting points and boiling points are, because it takes a lot to break them apart. The other thing that's important is it affects sort of solubility and how things mix with one another. So again, if you have somebody that's using hydrogen bonding and somebody that's using dispersion forces for the long period of time, they have no way to keep that interaction going. So for example, we take oil and vinegar salad dressing, right? You can mix it really good, but eventually what will happen is they'll kind of separate out from each other. And really it's because the oil is nonpolar, the sort of vinegar part is polar. So for a very short period of time, both can kind of put dispersion force, but they're not able to maintain that interaction. And basically everything will sort of separate out from one another. So that's what makes them relatively weak. Any questions on that there? All right, so obviously, as we talked about, the polarity of the bond also makes it really important. Even if you have a molecule that has nonpolar parts and a polar part, it can really affect solubility. So for example, if we look at something like this, which is ethanol, which is an organic alcohol. It actually has two parts to this molecule. It has this part, which is nonpolar. But what it does have is this OH bond, and that OH bond is polar. It's negative on the oxygen, positive on the hydrogen. And because it does have that OH bond, it actually is able to interact with water through hydrogen bonding from the negative oxygen to the positive hydrogen there. And it makes something like ethanol kind of soluble in water, even though it does have this. They have like a side that's like more non-polar. They have a side that, or a group that is polar, and it does allow it to interact. Now, mind you, if you happen to go up and just build out all more carbons and hydrogens, making that side much, much larger, what happens to the solubility is it goes down a lot. So when you hit about 6 carbons and something like that that has an OH group, the solubility drops way down to almost nothing. And that is because what happens is the nonpolar part is way too big. It gets in the way of the interaction between that and water. So it creates what's known as a steric hindrance. It's just like something that's really too big for the water molecules to get in there to interact with the OH part, and it decreases the solubility a lot. So let's talk about some examples of solubility in water. Obviously, if something is soluble, that means that they will mix. So if we're talking about a solid in a liquid, that typically means the solid will dissolve in the liquid. If we're talking about two liquids, it'll just look like one layer, right? And if something's insoluble, the solid will not dissolve in the liquid. And if you have two liquids, what will happen is you will get layering that will happen between the different liquids, right? They will kind of separate out from each other, kind of like what we did way back when those halogen reactions. In the fume hood, we had like the top layer and the bottom layer. Top layer, for example, in that case was, I think you guys use heptane maybe, or hexane, one of those, but the top layer was nonpolar and the bottom layer was polar. So over a long period of time, they had really no way to interact with each other. So what happens is, also what happens when you have like an oil spill in the ocean, the oil starts to float up. Oil is nonpolar and water obviously is polar, so they don't mix together. This ends up kind of separating out from one another. So when we talk about things that are soluble in water, definitely any ionic compound, like sodium chloride, ammonium nitrate should be soluble in water. Again, because they should break apart into their ions in water. They'll get surrounded by the water molecules like we saw earlier, and it will help it dissolve. But there's also, again, non-ionic substances, like I just drew kind of on the other page, things like sugar, things like ethanol. They also are going to be soluble in water. And again, even though they may have, like we just saw with ethanol, a part that's nonpolar, because they do have that OH bond in there, that allows it to interact well with water. Again, allowing it to really interact the same way water interacts with itself. And that's really what allows them to mix really, really well. Sugar, on the other hand, is a relatively big molecule, but as we will see, it has a lot of OHs in there, and that allows it to be really, really soluble in water. So here's the idea here. We have a water molecule. This is methanol, also an organic. So really, this side is nonpolar, but it does have this OH group there, which again is really that exact same OH group that we see in water. So they're able to interact really well through hydrogen bonding and make something like methanol going to be soluble in water because it does contain that OH group. It's going to allow them both to do basically hydrogen bonding with each other. So they're able to interact the exact same way. And there's ethanol that we drew before. Now, what about oil? Well, oil and water, they obviously do not mix. And it's really because oil is pretty much nothing but just a long hydrogens. I won't draw them all out, but the very long chain of carbons attached to carbons, which obviously carbon and carbon are the same. So electronegativity values are the same, which means it's nonpolar. And the bonds between carbon and hydrogen, electronegativity values is 0.4, which means it's also nonpolar. So what oil is, it's really just these long chain carbons. That's a nonpolar molecule. It's how we get things like gas and stuff like that. They thermally break it, basically from really long chains to smaller chains, like octane, like 8 of them, like gas, yes, and things to waxes and stuff like that. But the essence of oil is really just this really long, big, non-polar guy. So what it's trying to do, as I mentioned before, is because it uses dispersion forces as its main way of interacting. But when it comes to water, water basically wants to use hydrogen bonding. So once again, we're in that situation where they really can't maintain an interaction, a really stable interaction for any long period of time. Can they maintain it for a short period of time? The answer is obviously yes, but it will eventually separate out from each other. And that's really more because pretty much any molecule there is, be it polar, non-polar, whatever it may be, pretty much they all could use some type of dispersion forces. Although something like water, not dispersion, but everybody does have sort of the capability to do a little bit of dispersion forces, and that's why they're able to interact for a short period of time. But again, only through that very short sort of temporary interaction that will break apart. So it brings up the idea when we talk about solubility of like dissolves like. And what that means, again, is things with similar intermolecular forces will interact well with one another. So basically, things that are soluble typically are your ionic things and your polar things. Your polar and polar things are going to be soluble in each other. And the one sometimes people overlook, which is the nonpolar and the nonpolar, will also be really soluble in one another. And that's because nonpolar and nonpolar will both be using dispersion forces, which means they're using the exact same type of interaction that they use with themselves. So they will be actually soluble in one another. That is also why, if you think back to that experiment I was talking about earlier, the top layer was nonpolar, and what was up in the top layer was things like Cl2, Br2, which are nonpolar molecules. So that's why they ended up in the top layer, because they're more soluble in that experiment we did way back when. By the way, dispersion forces, strengths do increase with molar mass. So something that is a larger molar mass compound, if it's nonpolar, will have a stronger dispersion force than something that is smaller and nonpolar. And that's because something that is larger and nonpolar will have a lot more atoms. A lot more atoms means a lot more electrons and a greater chance of interaction and dispersion forces sort of moving around and creating that positive negative attraction. So really you only run into trouble though if you cross over kind of the polar, non-polar in most cases. So things that are insoluble, which means they won't mix, is really when you do cross over that polar to non-polar interaction. Those guys are kind of a no-go. And again, just the example of that is that test tube where we got the different layers between the polar and the non-polar. Any questions on that there? So here's sugar up on top. And again, although it is a really larger molecule, what helps it and aids it in being soluble is all these OHs pretty much littered all over the molecule. So everywhere there's an OH, it allows it to interact well with water. So even though it is a relatively bigger molecule, it is able to be soluble in water. As we know, if we take sugar and water, right, it will mix. This doesn't happen with oil, which is something like this down here, which is just all carbons and hydrogens, non-polar. It has nowhere on there for it to interact well with water. So again, it can only temporarily react. By the way, in addition to for something to be soluble in water, basically two things happen. And you have to break apart water and water interactions, right? And make room for whatever is coming in to basically be dissolved. So that's typically a very big molecule, which is not going to fit really well with smaller waters and stuff like that. So although it might work a little bit, it won't really work really well. So it's kind of like, you know, if you take like a semi truck and you try to park it into a garage, you could maybe get the front end in, maybe taking out the top of the building, but maybe get the front end in, but you aren't going to get obviously the entire thing into that area. So it's not going to really work very well. So smaller molecules that are non-polar but do have polar parts, you know, you could get it in there and they can interact well with one another. So here's again, typically what happens with our oil and water, and typically in chemistry, any type of organic layer is usually the top layer, and the aqueous sort of water layer is usually the bottom. So as you continue through chemistry, if you're ever separating out something that's sort of organic versus inorganic, use your organic layer there is up on top and your aqueous sort of water layers on the bottom. So speaking about solubility, let's talk a little bit about that. When one substance is dissolves in another, it is said to be soluble. So again, a lot of times we do sort of talk about solubility in terms of solid and liquid. So if something is soluble, it means it will dissolve. If something is insoluble, it will not dissolve, which is the next definition there. If something's insoluble in another substance, they will not mix together. Sometimes when people talk about sort of liquids and liquids mixing together, sometimes they talk about being miscible or immiscible. So if something is miscible, that is basically two liquids that mix together and are soluble. Something's immiscible, it is insoluble. So sometimes miscible and immiscible sort of relate to these two guys. And sometimes people use those terminologies for sort of liquid and liquid interaction. Now, there is usually a limit to the solubility of one substance in another. We'll talk a little bit about that in a second, but there are things that are always soluble in one another. So gases, because gases are basically flying around, they're constantly mixing with one another, so they're always soluble in one another. Liquids are also a lot of times mutually soluble. So again, that would be a polar guy, and a polar guy would be soluble in each other. A non-polar liquid would be soluble in each other. Again, if you cross over polar to non-polar, they will be insoluble in each other. Some other things that affect solubility, with that idea of like dissolves like, the solubility of a solute and a solvent can depend on temperature. Typically, the higher the temperature, the larger the solubility of a solid in a liquid, and that's sometimes what they tell you to do. If you can't get it to dissolve, kind of warm it up a little bit. When you warm it up, you're obviously increasing the temperature, increasing the energy, allowing things to move faster, a little bit more energy for that solid to start moving around a little bit more, and increasing the ability of it to sort of dissolve. At lower temperatures, you have a larger solubility of a gas and a liquid. And again, at lower temperatures, our gas molecules should be moving around slower, which means obviously your gas molecule, if it's moving slower, will stay in the liquid part a lot longer before it exits out. And that means that the liquid and the gas is more soluble in each other. In addition, when we talk about gases, it does depend on pressure. The higher pressure, the larger solubility of a gas in a liquid. The prime example of that is like a soda can, right? Before you pop it open, that can's under a lot of pressure. The CO2 is trapped in the liquid part because of that. Under the high pressure, the gas has a smaller volume, so it's in the liquid part of your soda. When you pop the top, right, you then release all that pressure. You also provide a hole in the top for the gas molecules to escape. That's the fizzing you see, that's the CO2 leaving, right? And because of that, the gas molecules can then escape the liquid and also your can. And that's also why when you come back later, your soda tastes really flat, because all your CO2 escaped through the top of it, right? And now you basically have syrup water, warm syrup water probably at that point. And again, that's what happens there. Sometimes what is referred to as Henry's law is that idea of the larger solubility of a gas in a liquid at higher pressures. Any questions on that? Now, there are a couple of ways that we do describe solutions, so let's talk about those. As I mentioned, there is a limit to how much you can get to dissolve, and it is based on temperature. So the solubility of a solute and a solvent is temperature dependent. And depending on the temperature, if you increase the temperature, you can probably get more solid to dissolve. And if you decrease the temperature, you can get less solid to dissolve. An example of that, I'm not sure if we did that experiment yet. I think we might have. We do the one where you just kind of shake the thing and the liquid goes back to solid. Yeah, no. And they in lab. Yeah. It demonstrated it. It was a beaker. I don't think we maybe did. Maybe it's today. I don't know. I should read the experiment. But might be today. But one thing that we do see is, you know, if you take a bunch of sugar, right, and you just keep pouring it into water, at some point, right, the sugar will stop dissolving and you'll just build up basically, you know, the sugar on the bottom there. So when we have basically the maximum amount of solute that will dissolve in a solvent, that is what is known as a saturated solution. And so the saturated solution basically is that point where you've hit exactly at that particular temperature how much solid will dissolve, which means if you continue to put solid in at that point, you pretty much will not allow it to dissolve. It'll just start piling up there on the bottom. The other case is what is referred to as an unsaturated solution. An unsaturated solution is what it sounds like. We haven't yet got there. So we haven't got to the point where the solute will stop dissolving, which means that if you continue to put salt in, it will continue to dissolve, and it will continue to dissolve until you hit saturated solution. So an unsaturated solution, you continue to put salt in, it will dissolve until you hit what is sometimes referred to as the saturation point. And at that point, you're at a saturated solution and it will no longer dissolve. Now there is, as I was talking about, as we might see in lab today, which I think it might be today's lab, there's something known as a supersaturated solution. And a supersaturated solution is oftentimes made by making a saturated solution and then heating it up. And as you heat it up, what that's going to do is allow really more solute to dissolve in there because you increase the temperature. And typically after you heat it up, you're able to get a lot of solid to dissolve because it's a really hot solution at this point. So the solubility of that solid goes up. Then what happens is you kind of just let it cool down naturally. You really don't touch it or anything like that. And what happens is as it starts to cool back down, the temperature is dropping, which means the solubility is also coming back down. But you've already dissolved all your solid in there. So at this point, what you have is as it cools back down, our solubility goes down, which means you have, in this case, a supersaturated solution that has too much solid dissolved in it. In addition to increasing the solubility of the solid that was dissolved in there, as you're heating it, you're also evaporating off some of the water, which is a solvent. So you now have a little bit less water. You got too much solid in there. And what that creates is a really unstable solution. And it's so unstable because, like I said, you pretty much have way too much dissolved in there. It's so unstable, as I mentioned, as maybe we'll see, if you just kind of knock it by accident, basically all the solid will come out of the solution. Or if you just take one super small little like grain or whatever was dissolved in there and you just like drop it in there, what will happen is it will realize I have way too much solid dissolved in this liquid. And what you'll start to see is all the solid will start to come out of solution and you'll end up with a rock hard solid at that point. So a supersaturated solution is one where basically you get to a saturation point, you kind of increase the temperature to allow solubility to increase, you continue to dissolve, but then as you cool it back down, the solubility starts to decrease and you end up with way too much dissolved in a solvent, creates a very, very unstable sort of solution. Any questions on that? I think we will see it coming up. So a couple other ways to describe solutions is concentrated. A concentrated solution is also sometimes referred to as a stock solution. It is a solution that has a relatively large amount of solute in it. So it's pretty strong, as opposed to a dilute solution, which is a solution that contains a relatively small amount of solute in there. A lot of times in the laboratory, we use obviously dilute solutions. And as we'll talk about, basically to make a solution, you basically just add more solvent or water in a lot of cases. And what that does is it makes it less concentrated. So like if you got your soda before class, right, with all your ice and it tastes really good, come back after class and it's been sitting in your car, right, all the ice melts, right, it dilutes down all the syrup and all the good stuff in your soda and you taste it and it does not taste right. It tastes really, really diluted. And that's sort of the idea there, obviously, of dilution. Any questions on any of that stuff there? All right, we're going to talk here about some important concentration units for solutions. So the first one we're going to talk about is what is referred to as mass percent or mass percent. So this is sometimes abbreviated as percent mass to mass. And to calculate the percent mass to mass, you take the mass of the solute. So that is the smaller part of the solution divided by the mass of the solution times 100%. Now, when people do these calculations, it is the bottom part here that you do have to be really careful of. And that is because the mass of the solution is actually two things. It is the grams of the solute and the grams of the solvent. And I say that because very often in percent mass to mass sort of calculations, they will give you those numbers separate. So they'll give you like the mass of the solute, they'll give you the mass. So it's very, very common mistake that people make is they just grab the solvent and they use that in the calculation, again, without obviously getting the entire solution. So you do want to watch that when you're doing percent mass to mass. What does that mean? Sometimes you are given the percent mass to mass, and you can plug it into this formula here. But if you're given 3.75% mass to mass of sodium chloride, you could take that if you wanted to do more of a dimensional analysis calculation. You could convert that into sort of some usable conversion factors. So as you know, whenever you have a percentage, you want to kind of use it as a number. You could assume 100. So what that would mean is, in this case, we would have 3.75 grams of sodium chloride in 100 grams of solution. Or we could use it as a conversion factor. 100 grams of solution gives us 3.75 grams of sodium chloride. So if you want to sort of take more of a dimensional analysis approach, if you are given the percentage, you could turn them into conversion factors by assuming 100 grams in this case, and just do it that way. Otherwise, you can obviously plug and chug into this equation here, and you could get obviously the answer that you're looking for. So let's take a look at a couple of other ones that kind of go with this. There's also percent volume to volume, like in alcohol. That is the volume of solute divided by the volume of solution times 100%. And there's also percent mass to volume, which is the mass of the solute over the volume of solution times 100%. And we could add our one that we saw earlier, obviously our mass to mass, which is our mass of our solute, mass of solution times 100%. So these are three sort of percent concentrations that we can use, and they all kind of work the same way. The only one that you really have to worry about, like I said on the bottom there, is usually this one, because that is usually given separately. The volume of solution in both of the top one and the middle one is usually just given to you a lot of times in the problem, so you don't usually have to worry about sort of is that the solute or the solvent. Now, for all these, we can basically turn them into usable conversion factors if you needed to. So we'll use our same example that we had before. Let's say we had a 3.75% volume to volume sodium chloride, a 3.75% mass to volume of sodium chloride, and like we saw just a second ago, 3.5% mass to volume sodium chloride here. I'm sorry, mass to mass. So as we saw before, we could do 3.75 grams of sodium chloride over 100 grams of solution, or 100 grams of solution over 3.75 grams of sodium chloride. For this guy here, we could say that there is 3.75 milliliters of sodium chloride over 100 milliliters of solution. Our 100 milliliters of solution, there is 3.75 milliliters of sodium chloride. And for the middle one here, 3.75 grams of sodium chloride over 100 milliliters of solution, or 100 milliliters of solution grams of sodium chloride. This one here is kind of like density, right? Grams per milliliter is basically what we got going on there. Volume to volume is milliliters over milliliters typically, and obviously mass to mass is grams over grams. Any questions on any of those? Again, for all those, you can stick it back into the original formula and solve it that way. Or again, if you want to do more of a dimensional analysis approach and you're given the percentage of them, you could turn them into sort of a usable conversion factors. Any questions on any of that there? All right, let's try one here then. Right there. Let me just write over that there. So let me get rid of that there. All right, let's try that. All right, a solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. calculate the mass percent here. So we're looking for the percent mass to mass here. Look here. So in this particular case, obviously we're looking for the mass percent, which once again is the mass of the solute divided by the mass of the solution times 100%. In this case, we're taking 2.5 grams of calcium chloride and mixing it with 50 grams of water. My solute would be the calcium chloride, right? That would be my solute. That is the smaller part. My solvent in this case would be the larger part, which is the water. That means that the mass of the solution, which is the important part here, is actually going to be 50 plus 2.5 grams, not 50 grams. That will give me 52.5 grams as the mass of the solution. Again, if you use just 50, that is just the solvent and would be incorrect in this case. So to figure out the percent mass to mass, it would be our 2.5 grams divided by the total mass of the solution times 100% in this case, which would be 2.5 divided by 52.5 times 100, about 4.76% by mass. And you could leave it as like calcium chloride there. So in this case, it is a percentage of sort of the units that we get here as the grams of grams cancel. And you could do parentheses m/m. Any questions on that there? Yeah. Why don't you do the solute minus solvent? Is that what you're asking? Yeah, so we're looking for the solution. So the solution in this case, in any case, a solution is basically the solute plus the solvent. So that's basically the definition of a solution, is basically those two things added together. It's basically the smaller part that you dissolve and the larger part that you mix it with. And those two together, once they're all mixed, gives you the mass of the entire solution. And again, I would say these type of problems with specifically mass to mass percent are sort of historically known to be, they give you that information separate from each other, the solute from the solvent. So again, it's a very common error that people make, is they just kind of go with just a solvent by itself. I would say the other percentages, like I talked about, you don't have to worry too much about that, because a lot of times they'll just say, hey, you know, you have 400 milliliters of solution or something like that. So they don't usually kind of break up the solute from the solvent, and when you're dealing with something volumes, but definitely with grams, they very commonly will. Other questions? Okay. All right, so I'm gonna try this one here. Concentrated hydrochloric acid is 37.2% by mass, HCl. What is the mass of the HCl in 35.5 grams of the concentrated HCl solution? Okay, let's take a look. So in this case, we have the percent mass to mass given to us, which is 37.2%. We are looking for the grams of HCl, which is our solute. And we have the mass of the solution given to us, which is 35.5 grams of HCl, basically. So you may be wondering, how do I know that that is basically our mass of the solution and not the solute? And that's because we're looking to find the grams of the HCl. So I do know that the name of the solution is the solute. So that is what we're looking for, obviously, if we're looking for the HCl. So that's why I know that this is actually the solution part of it. We can do it two ways. We could plug it into the equation. We also could do more of a dimensional analysis approach. So I'll show you that way here. So that means that there are 37.2 grams of HCl and 100 grams of solution. Or in 100 grams of solution, there are 37.2 grams of HCl. So if I took my mass of the solution, which is 35.5 grams of solution, I use this as a conversion factor where 100 grams of solution would go on the bottom, 37.2 grams of HCl would go on the top. The grams of solution would cancel, and that would get me 35.5 times 37.2 divided by 100 gives me 13.2 grams of HCl would be dissolved in there. HCl would be dissolved. First up, any question on that there? Now, again, you could absolutely plug and chug into this equation that we saw, and you will get the same answer because, frankly, you're doing the same math. So you could do the same thing and just put it into this equation, which would give you obviously 37.2% would equal the mass of the HCl divided by 35.5 grams of solution times 100%. You would, multiply by 35.5 to the other side and also divide by 100%, right? Percentage will cancel and you'll end up obviously here as well. So they're both really the same math, just one's more of a dimensional analysis approach and one obviously it's just plug and chug into the equation, and obviously we should get you to the same spot. Any questions on any of that there? Okay, now these percent concentrations are common concentrations, but very less common than probably the major unit of concentration that we see for solutions, and that is actually molarity. So molarity is really, I would say, probably the biggest unit of concentration that you see, the most common unit. Molarity is abbreviated with a big M, and it equals moles per liter. It is actually, as it says here, moles of solute per liter solution. You could think of molarity as like a formula because oftentimes we do use molarity and volume and to solve for any of these things. So you may solve for moles, you may solve for liters, or you may solve for molarity. So if you wanted liters, it would be moles divided by the molarity. And if you wanted moles, it would be liters times the molarity. And I would say that is something that's used a lot in chemistry, figuring out moles from volume and molarity. Definitely used a lot. Now, when we do have something that is, say, 4.25 molar sodium chloride, and that's what that means. 4.25 big M sodium chloride means 4.25 molar sodium chloride. If you were going to do a calculation using this number, it is very highly recommended that you get rid of the big M and you use both units. And what that would mean is you would have 4.25 moles of sodium chloride per liter. So the number always stays with the moles part, and it's always 1 liter. And I would highly recommend that you get rid of the big M in calculations and show both of those units. You could also use it as a conversion factor if you want to flip it the other way around, put liters up on top. You're going to do some dimensional analysis, 4.25 moles on the bottom. The reason why I say you should get rid of the big M is this. People leave the big M in their calculations and they have no clue as to where volume is, or even if there is volume. So sometimes people see the big M and all they think is moles, and it's not moles, it's moles. Then they have no idea if they maybe do realize that there is volume. They have no idea, should they be like multiplying or dividing and where it is. So if you put both of the units there and sort of do more of a dimensional analysis calculation, you will be able to see both of the units and make sure you don't kind of miss it. 100% of the time, if you want to calculate moles and you're using molarity, you should always convert your volume into liters, because when you do take liters times molarity, basically what you're doing is taking liters times moles per liter. Those cancel and leaves you moles. If you multiply milliliters times molarity, you do not get moles. You actually get what is referred to as millimoles, which some people do, and it's sometimes okay to do, but people sometimes do not realize that if they do this move, they actually end up with millimoles and not moles, which is a factor of 1,000 off if you're thinking moles. And that's okay, because if you do actually divide by milliliters, the milliliters cancel and it becomes moles per liter again. So I would highly recommend in any situation, if you're using solely molarity by itself and volume, those are the only two things you're using in the calculation, you should always convert to liters. You'll always probably get the right answer you're looking for. In most cases, people are not usually looking for millimoles, they're usually looking for moles. There is a formula that we'll see a little bit later on where it's okay to leave them in milliliters, but that's specifically for that formula. But you should always just be safe and convert it to liters. And in any case, you'll always be safe if you convert it to liters. You'll probably be in the right units that you're looking for. Any questions on that there? How do we get these things? A couple of ways. Obviously, the volume is the volume. The moles are sometimes just given to you in moles, or sometimes you need to convert grams to moles using the molar mass like we've done before. So that's, again, how you could kind of get the moles part. So a solution is 1 molar, and it contains 1 mole of a solute per liter of solution. How does concentration and ions sort of work together, an ionic compound? Well, how it works is basically like this. If you have sodium chloride, for example, and it's a solution, and this guy was 1 molar, when this guy breaks apart in solution, as we talked about, it really is not going to stay together. It's going to break apart into a sodium ion and a chloride ion. And the way concentration works in terms of the whole ionic compound to really the ions in solution, because this is an ionic compound, this is pretty much what you do have in the actual solution floating around. It is like stoichiometry. It is a 1-to-1 relationship between these two, which means if you wanted the concentration of just the sodium ions that are floating around in that solution, it would be 1 times 1 molar, which means it would also be 1 molar of sodium ions. Same thing here. It is a 1-to-1 relationship between the whole thing and chloride, which means you take 1 times 1 molar, and you will get 1 molar chloride ions. So the concentration is related to the ions based on how much they break apart. So for example, though, if we had, say, calcium chloride here, and we had the same 1 molar concentration, when calcium chloride breaks apart, it breaks apart into a calcium ion and 2 chloride ions. That means it is a 1-to-1 relationship between these two, which means the concentration of calcium will be 1 times 1 molar, which would be not 2, 1 molar. Now, when we look at calcium chloride to chloride, it's a 1-to-2 relationship. You get twice as much chloride for your buck there every time it goes in, which means we would actually take 2 times the 1 molar. And the concentration of the chloride ions in that solution would actually be 2 molar. So you can see concentration is not additive. You add 2 and 1 together, you don't get 1, but it is proportion wise. So every time you drop a calcium chloride into solution, you get 1 calcium for every 2 chlorides, which means it's twice as concentrated in terms of the chloride, and that's how it's reflected in the concentration. Any questions on that? Obviously, if it broke apart into a 1-to-3, you would multiply the concentration by 3. This would be if you're interested in just the ions concentration of what's floating around. This is the short way of doing it. Let me show you the long way calculation so you understand really how we get there. So for example, here, if we started with 1 molar calcium chloride, that would be 1 mole of calcium chloride per liter of solution. Doing stoichiometry just like normal, it is a 1 mole of calcium chloride to a 1 mole of calcium. The moles of calcium chloride cancel, leaves us with 1 mole of calcium ions per liter, which is 1 molar calcium ions. We do the same thing for the chloride, 1 mole of calcium chloride per liter. Doing the stoichiometry for our calcium chloride, 1 mole of calcium chloride is 2 moles of chloride. Moles of calcium chloride cancel, gives us 2 moles of chloride per liter, are 2 molar chloride. So this is the stoichiometry, which is what we're multiplying by here. That's a 1-to-1 relationship. That's a 2-to-1 relationship. So the quicker way is just to multiply by the coefficient. or you could do the long calculation, but that's essentially how you go from the whole thing to each of the individual ions. Any questions on that there? So sometimes you may not be interested maybe in the whole solution, but really what the concentration of, let's say, an individual ion that's maybe floating around. And again, this is sort of how you could sort of figure that out. Any questions on that there? Okay. All right, so why don't we try one here? Calculate the molarity of a solution prepared by dissolving 15.6 of potassium bromide in enough water to make 1.25 liters. Since we're getting to the end here, we'll do this together. Potassium there is, I think, 3910. Bromine is 7990 from the periodic table. So we do want to calculate the molarity here. So molarity is moles per liter. So if we look at what we obviously have the liters part given to us, which is 1.25 liters. And the other thing that we have is 15.6 grams of KBr. And that's okay because we do know how to go from grams to moles, which is essentially what we need, right, to actually calculate the molarity. So that's what we would want to do. We would want to convert our grams of KBr into moles using the molar mass from the periodic table. So we're just going to add those together. 3910 plus 7990 gives us 119 grams per mole when we add those together. So that's grams there. 119 grams per mole of KBr. The grams will cancel each other out. We will have 15.6 divided by 119 gives us 0.131 moles of KBr, which is basically the top part of what we need. Now to calculate the molarity, we're just going to put those numbers together. 0.131 moles per 1.25 liters. So 0.131 divided by 1.25 gives us 0.105. Now, in terms of the units, they do not cancel, so you could leave it as moles per liter. Again, the number always goes with the moles. It's always 1 liter, and you could put KBr. Or you could write 0.105 big M KBr. So either one is obviously acceptable here. So this is a very common way that you calculate molarity. The other thing that you might have to do is liters to milliliters to liters. So again, that's your 1,000 milliliters to a liter. Any questions on any of that there? All right, we will lay it up there.